properties of modulus of a complex number. So the first property says modulus of z is equal to modulus of z bar. Now if z is equal to x plus iy, modulus z is equal to root of x square plus y square. Your z bar is equal to conjugate of z is x minus iy. So modulus of z bar is equal to root of x square plus minus y the whole square. This is also equal to root of x square plus y square. Therefore, modulus z is equal to modulus z bar. Now the second property says modulus of z1 plus z2 is less than or equal to modulus z1 plus modulus z2. Now if you are plotting it in a diagram, in an organ plane, if there are two complex numbers, let OA represent z1 and OB represent z2. If you are going to complete a parallelogram, say you are completing a parallelogram, so now this is equal to z2, so this also will be equal to z2. Now if you are going to join the diagonal OC, now this OC is equal to, by vector addition, we are going to get OC vector is equal to OA plus AB. OA plus AC. OC is a third side of the triangle. So OC vector is equal to OA vector plus AC vector. So OA is Z1 and AC is Z2. So OC vector modulus, the length of OC is modulus OC vector is equal to modulus of Z1 plus Z2. We know that in a triangle, sum of the two sides is always greater than the third side. Therefore, modulus Z1 plus modulus Z2 is greater than modulus Z1 plus Z2. So this represents the third sides. So it can never be less. It should be always, sum of the two sides of the triangle is always greater than or equal to the third side. It can never be lesser. Or this can, in turn, you can write modulus of Z1 plus Z2 is less than or equal to modulus Z1 plus modulus Z2. The third property says modulus Z1 Z2 equal to modulus Z1 into modulus Z2. The fourth property again, modulus Z1 minus Z2 is greater than or equal to modulus Z1 minus modulus Z2. Here we are going to take the real axis and imaginary axis. This is your real axis and this is your imaginary axis. So if you are going to plot one point, P is equal to Z1 and Q is equal to Z2. This is Z1, modulus Z1, this is modulus Z2. Now sum of the distance between P and Q is nothing but Z1 minus Z2. The difference between the two lines is given out to be PQ is nothing but the difference between the OP and OQ. Therefore, this distance is nothing but modulus of this. So, this is always greater than or equal to these two. So, this difference is always greater than or equal to Z1 minus Z2. So, So modulus of Z1 minus Z2 is always greater than or equal to modulus Z1 minus modulus Z2. We also have the fourth property, modulus of Z1 by Z2 is equal to modulus Z1 by modulus Z2, and modulus Z power n is equal to modulus Z the whole power n, where n is an integer. Now real of Z is the seventh property says real of Z is less than or equal to modulus Z. We know the value real of Z is equal to only x. If Z is equal to x plus iy, we know that real Z is only equal to x, and modulus Z is equal to x square plus y square, root of x square plus y square. So this value, since as there is no y, so this value is, x is always less than this value, hence real Z is less than or equal to modulus Z. Same way imaginary Z is also less than or equal to modulus Z. For the same reason, imaginary Z is equal to y. Therefore, y is less than root of x square plus y square. Now these properties are very important as we use them when doing the exercise. Now let us do triangle inequality. Using all these properties, let us prove the property modulus Z1 plus Z2 is less than or equal to modulus Z1 plus modulus Z2, and this property is known as triangle inequality. To prove this, we are going to assume, see, we also know that the modulus Z is equal to root of x square plus y square. Same way, modulus Z bar is equal to, Z is what, x plus iy, and Z bar is x minus iy. This also we get it as x square plus y square. So modulus, so this square modulus, therefore we are going to get modulus Z the whole square is equal to Z bar. So we are going to use this result to prove the triangle inequality modulus Z1 plus Z2 is less than or equal to modulus Z1 plus modulus Z2. Now modulus Z1 plus Z2 the whole square. Using this formula, we are going to get Z1 plus Z2 into Z1 plus Z2 the whole bar. Now this is equal to Z1 plus Z2 into Z1 bar plus Z2 bar. We can multiply this and write Z1 bar plus Z1 Z2 bar plus Z2 Z1 bar plus Z2 Z2 bar. Now Z1 Z1 bar is equal to this formula, modulus Z1 square. Now this is plus Z1 Z2 bar plus Z1 Z2 bar the whole bar. So that, see, when we take out the bar, this will become Z1 bar, and Z, we know that Z bar the whole bar is equal to Z. So we get back this formula. So this is equal to plus Z2 bar is equal to modulus Z2 square. See, now this can be rewritten as, say, grouping these two. Now this can be rewritten as modulus Z1 square plus See, we have this, if you are going to consider this as whole z, we have z plus z bar. Now z plus z bar is equal to 2 into real of, this is equal to 2 into real part of z1 z2 bar plus modulus z2 the whole square. What is the reason? Since we know that z plus z bar is equal to 2 real z. This is the formula we have learned already. So z bar is equal to 2 into real z. Now instead of z we have z1 z2 bar. So we have 2 into real z1 z2 bar. Now this is less than or equal to, see, if you are going to take the whole, this is equal to modulus z1 square plus 2 into z1 z2 bar. See, we are only having z1 z2 bar, so this must be less than, if you have plus the imaginary value, so plus modulus z2 square. So now this can be written as, now this is equal to, what do we get here? This value must be equal to a square to ab plus b square. So this is equal to modulus z1 square plus modul 2 into modulus z1 into modulus z2. See, modulus z2 bar is equal to modulus z2. Therefore, we can, instead of writing modulus z2 bar, okay, let's write one more sentence, z2 bar plus modulus z2 square. Now, this value is the same. This is equal to modulus z1 square plus 2 into modulus z1 into z2 bar is equal to, modulus z2 bar is equal to modulus z2. Therefore, we can write this as modulus z2 plus modulus z2 the whole square. This is a square to ab b square. So, already this is less than or equal to. Therefore, it is less than or equal to z1 plus z2 the whole square. So, modulus z1 plus z2 the whole square is less than or equal to modulus z1 plus modulus z2 the whole square. Taking the square root on either side, we get modulus z1 plus z2 is less than or equal to modulus z1 plus modulus z2. This inequality is known as triangle inequality. In this exercise, the first question, we are asked to find the modulus of the given numbers. Now let us assume z is equal to 2i divided by 3 plus 4i. Now taking modulus on either side, modulus z is equal to modulus 2i divided by 3 plus 4i. We know that modulus z1 by z2 is equal to modulus z1 divided by modulus z2. Therefore, this will become modulus 2i by modulus 3 plus 4i. Now, modulus 2i is equal to root of 4, x square plus y square. Here x square is 0, so 0 plus 4, it is 4. Denominator, it is going to be root of 3 square 9 plus 4 square 16. So, this is equal to 2 divided by root 25. So, this is equal to 2 divided by 5. So, modulus z is equal to 2 by 5. In the next question, we have z is equal to 2 minus I by 1 plus I plus 1 minus 2I by 1 minus I. Now this is equal to, taking LCM, 1 plus I into 1 minus I. So 2 minus I into 1 minus I plus 1 minus 2i into 1 plus I. Now multiplying, we get 2 minus 2i minus I plus I square plus 1 minus 2i plus I minus 2i square divided by 1 square minus I square. So this is equal to 2 minus 1 minus 3i plus here 1 minus 2 gives you minus of minus plus 2 plus 1 gives you plus 3 minus I divided by 1 plus 1. So this is equal to 4 minus 4i divided by 2. So if taking 4 common outside, 1 minus I divided by 2 gets cancelled. So this is equal to 2 into 1 minus I. Therefore, modulus of Z is equal to modulus of 2 into 1 minus I. So this is equal to 2 into modulus of 1 minus I. This is equal to 2 into root of 1 square plus 1 square. This is equal to 2 into root 2. So modulus Z is equal to 2 into root 2. The next question is 1 minus I the whole power 10. Let us take Z is equal to 1 minus I the whole power 10. Therefore, modulus Z is equal to modulus 1 minus I the whole power 10. Now, by the property, we can take the power outside. So, modulus 1 minus I the whole power 10. Modulus 1 minus I is root of 1 square plus 1 square the whole power 10. So, this is equal to root 2 power 10. That is equal to 2 power 5. This is equal to 30. For any two complex numbers Z1 and Z2 such that modulus Z1 is equal to modulus Z2 is equal to 1 and Z1 Z2 is not equal to minus 1, then show that this is a real number. Z1 plus Z2 by 1 plus Z1 Z2 is a real number. Now, to show that it is given modulus Z1 is equal to 1, therefore modulus Z1 the whole square is equal to 1 square, that is equal to 1. Now modulus Z1 square we can write it as Z1 bar is equal to 1. Therefore Z1 is equal to 1 by Z1 bar. Okay. Similarly, modulus Z2 square is equal to 1 gives Z2 is equal to 1 by Z2 bar. Okay. Now substituting in the question, we have Z1 plus Z2 by 1 plus Z1 Z2 is equal to 1 by Z1 bar plus 1 by Z2 bar divided by 1 plus 1 by Z1 bar into 1 by Z2 bar. Now this is equal to taking LCM. We get Z1 bar plus Z2 bar divided by Z1 bar into Z2 bar whole divided by Z1 Z2 plus 1 by Z1 bar Z2 bar. So denominator gets cancelled. We get the answer as Z1 bar plus Z2 bar divided by Z1 bar Z2 bar plus 1. Now Z is real only when Z is equal to Z bar. So now this is your Z. So this can be written as therefore Z1 plus Z2 divided by 1 plus Z1 Z2 can be written as Z1 plus Z2. See, Z1 bar plus Z2 bar can be written as Z1 plus Z2 the whole bar. Same way here divide by here we will be getting Z1 Z2 plus 1 the whole bar. z1 plus z2 divided by 1 plus z1 z2 is equal to, we are getting z1 plus z2 by 1 plus z1 z2 the whole bar. See, taking the z1 bar by z2 bar can be written as z1 by z2 the whole bar. Using that property, we can take this bar outside and we can rewrite this as z1 plus z2 by 1 plus z1 z2 the whole bar. Therefore, z1 plus z2 by 1 plus z1 z2 is a real number. The next question is, which one of the points is closest to 1 plus I? Let us take, let A is equal to 10 minus 8i, B is equal to 11 plus 6i, and C is equal to 1 plus I. Let us try to find out, see which is closer. Suppose the point C is, where there is a point A, it's a point B. We are supposed to find out which is closest. Here's the point C. So we are supposed to find out what is AC and what is BC. Whichever is shortest, it will be closest to the point C. So to find AC, we get AC vector is equal to OC minus OA. So OC is given to be modulus 1 plus I minus 10 minus 8i. This is equal to 1 minus modulus 1 minus 10 gives you minus 9 plus I minus of minus plus 9. Right. So this is equal to root of 81 plus 81. This is equal to root 162. This is your AC value. If you are going to find out BC, the BC is equal to modulus. What is your OC minus OB? This is equal to mod of OC is 1 plus I minus 11 plus 6i. This is equal to mod of 1 minus 11 gives you 12. 1 minus 6 gives you minus 5i. So this is equal to root of 144 plus 25. So the root 169. So now which is the shortest? 1 minus 11 here. This will be minus 10. 1 minus 11 minus 10. Then 1 minus 6 minus 5. So this is equal to 100 plus 25, and this is equal to 125. So BC is equal to 125, AC is equal to root 162 definitely, which implies BC is shorter, 125 is less than 162. Therefore, B is closer to C. The next question is, if modulus Z is equal to 3, show that 7 less than or equal to Z plus 6 minus 8i less than or equal to 13. Here now to find the lower bound and upper bound. To find lower bound and upper bound, we have the inequality modulus Z1 minus modulus Z2 is less than or equal to modulus Z1 plus Z2 less than or equal to modulus Z1 plus modulus Z2. Now Z1 modulus Z1 is limited to this, we take it as lower boundary Z1, and 6 minus 8i we take it as Z2. So we get here modulus 3 minus modulus 6 minus 8i is less than or equal to Z1 modulus 3 plus Z2 is 6 minus 8i is less than or equal to modulus Z1 plus Z2 modulus 3 plus modulus 6 minus 8i. So this is equal to modulus 3 minus, this is going to be 636 plus 64 is less than or equal to modulus Z plus 6 minus 8i is less than or equal to 3 plus root of 36 plus 64. This is modulus 300 root 100 is equal to 10 is less than or equal to modulus Z plus 6 minus 8i is less than or equal to 3 plus 10. So 7. So this is equal to 7 less than or equal to modulus Z plus 6 minus 8i less than or equal to 13. If modulus Z1 is equal to 1, show that 2 less than or equal to modulus Z square minus 3 is less than or equal to 4. So modulus Z is equal to 1 implies modulus Z square is also equal to 1. Therefore, we know that the identity modulus Z1 minus modulus Z2 is less than or equal to modulus Z1 plus Z2 is less than or equal to modulus Z1 plus modulus Z2. So now modulus Z1 is equal to modulus Z1 square minus Z square your Z2 is 3 minus modulus 3 is less than or equal to modulus Z square minus 3 is less than or equal to modulus Z square plus modulus 3 square. So this is equal to modulus Z square is 1 minus 3 less than or equal to modulus Z square minus 3 less than or equal to 1 minus 3 square. This is equal to modulus 3 modulus Z square minus plus modulus 3. It's not a square. Modulus 3 that is equal to Z square is 1 minus 3. So this is going to be minus, this is equal to modulus minus 2 less than or equal to modulus Z2 Z square plus modulus 3. So this is equal to Z square minus 3 less than or equal to 4. So 1 minus modulus 3 is modulus minus 2 is equal to 2 less than or equal to modulus Z square minus 3 less than or equal to 4. So here we are taking Z squares, here it is given Z square minus 3, hence we are finding modulus Z1 is equal to 1, therefore Z1 square is also equal to 1. So our lower point will be modulus Z1 minus Z2 is less than or equal to modulus Z1 plus Z2 less than or equal to modulus Z1 plus modulus Z2. Here our Z1 becomes Z1 square and Z2 value becomes 3. Just substitute, then take the modulus, we get 2 less than or equal to modulus Z square minus 3 less than or equal to 4. In the next question, if modulus Z minus 2 by Z is equal to 2, show that the greatest and the least value of modulus Z are root 3 plus 1 and root 3 minus 1. So we know that modulus z minus modulus 2 by z is less than or equal to modulus z minus 2 by z is less than or equal to, oh, this is equal to 2 given, equal to 2. So this implies modulus z minus modulus z 2 minus z modulus z minus modulus 2 by z is less than or equal to 2. Now if you are going to replace, let us consider we are supposed to find out the lower and the upper limit. So if you are going to consider the first case, t is equal to modulus z, this will reduce to t minus 2 by t is less than or equal to 2. So t square minus 2 is less than or equal to 2t, or t square minus 2t is greater than or equal to 2. So t minus 2 by t less than or equal to 2. So modulus of 2 minus, substituting here, modulus of t minus 2 by t is less than or equal to 2 implies minus 2 less than or equal to t minus 2 by t less than or equal to 2. So the value of t lies between minus 2 and plus 2. So this is equal to, if t minus 2 by t is equal to 2, then we get the equation t square minus 2 is equal to 2t. Therefore t square minus 2t minus 2 is equal to 0. So t is equal to minus b plus or minus root of b square minus 4ac divided by 2a2. So this is equal to 2 plus or minus root 12 divided by 2. Taking 2 as LCM, common factor, 1 plus or minus root 3 divided by 2. So t value is equal to 1 plus or minus root 3. Therefore t is modulus z. So minimum value of mod z is equal to mod 1 minus root 3, and maximum, this is equal to this maximum is equal to, maximum value is equal to mod z is equal to mod of 1 plus root 3. So now this is equal to root 3 minus 1. So this value is equal to 1 plus root 3. Therefore the maximum value is root 3 plus 1 and minimum value is root 3 minus 1.